welcome everybody to this wonderful talk we're about to hear. So yeah, as I was just introduced, my name is Jed Pixley. I'm an associate professor in physics at Rutgers University. So welcome to the free physics talk in honors of Heinz Pagels, who supports this. And so I've been coming, as was just said, for about 9 years. Been in town now for almost 2.5 weeks, which is absolutely fantastic. Let me just start by thanking you all for welcoming us into your town, into your homes. Makes a big difference. The center, it really helps us function in general. So this year, I actually brought my family. My kids have been enjoying the camps at Snowmass, having a fantastic time. From my perspective, I get to have a very creative scientific endeavor here. My family's enjoying the mountain. For me, it really takes away a lot of life's worries and allows you to really and dive into new ideas in science and try to do things you'd never tried to do in your everyday life. So just thank you again. And tonight we're really fortunate to have our speaker, Raquel Queiroz, with us, a fellow organizer of this workshop that was just introduced, which is quantum matter through the lens of Moiré materials. And we're going to hear a little bit about those words here today. Moiré is because we're taking two-dimensional materials and twisting them, our experimental colleagues are twisting them, creating a Moiré pattern, a word from French, just about the interference of those two images. So Raquel is an assistant professor at Columbia. She got her PhD at Stuttgart. It's a solid-state physics Max Planck Institute, and then a postdoc at the Weizmann Institute in Israel. And her research, broadly defined, uses the mathematical notion of topology to describe quantum materials. And she's going to tell us a little bit more about that today in her lecture on the geometry of quantum matter. So Raquel, please take it away.
What I'm going to tell you today about is actually a relatively new field. It is at least a reformulation of quantum mechanics in a sense. And discussions here these 2 weeks have been extremely important, even to make these ideas sharper. So I will tell you about quantum mechanics, but I will tell you not about quantum mechanics of a single particle, but quantum mechanics of billions and billions of particles together, right? Because this is how matter is made of. Matter is made of 10 to the 23 particles of the order, right? So it's infinitely many particles together. And really things start behaving very differently when you have so many particles together. And what has come up in the recent years, or maybe the recent couple decades, to our understanding is that mathematical concepts such as geometry are extremely important. Geometry and topology are extremely important to understand these things. For example, if I want to talk about how heavy is an electron when it is in a material, I need to talk about some geometric concepts. And I will try to describe that to you today. Okay? But so if I want to talk to you about quantum mechanics, I have to tap a little bit into your intuition of waves, because quantum mechanics is all about waves. So one wave that we understand very well is sound waves, right? So that's just pressure waves in the air that we are going to be able to hear. So you can see here, as the time passes, which is changing, right? The amplitude of the wave is changing. And we will hear a tune, which is going to be basically telling you what is the frequency of this wave. Okay. You might have perfect pitch and see that this is C, or you can just read it over here. Okay, so we are very, very good in understanding this type of very detailed frequencies. Okay? Let me do something else. Let me play it again. Did you hear it? It was just a fraction of a second. You can hear it again. Okay, very hard to tell which tune is playing, right? Let me play it again. Almost the same. In fact, this last time, I played a D. Right? So see that we are amazing in understanding the differences between these two frequencies, but actually they just differ by fractions of milliseconds in their frequency, in the rate of how they change in time. And it's really amazing how we are able to see these differences. We are able to understand these differences if we let the tune play for enough time, right? So it is important that time is passing. And why is that? Because frequencies, fundamentally what it is the rate of change in time. So by definition, I could not possibly tell you which tune is playing if I tell you the timestamp at which I play this. So this is really a concept that, you know, if you're interested in physics, you all came here tonight. So you probably heard of the uncertainty principle, the Heisenberg uncertainty principle. It's a really classical phenomenon. This is just uncertainty because what I'm saying is that if I know the tune, the frequency, I don't know which time it was played. If I know the time it was played, I don't know the frequency because it's the frequency is the rate of change in time. So there's basically, if I'm uncertain in which time it was played, I will have some uncertainty in which frequencies have composed that sound. And there's another important quantum mechanical concept, which is really just about how waves behave, which is the concept of interference. So let me now play again these periods here. These are associated with the frequency. So it tells you which tune it's playing. There's two waves here, one white and one blue, playing on top of each other. And if they are exactly in what's called in phase, they have played exactly at the same time, then we will have constructive interference. What does that mean? Is that you just hear it louder, double the amplitude. But with the exact same energy, with the exact same frequency, I could just put them out of phase with respect to one another. Here you see the blue just shifted to the white. And when I would add them up, you will hear mute. This is really a property of how waves add up and how they interfere with each other. We call this guy constructive interference, destructive interference. And if you are to play two frequencies, two sounds, which are extremely similar in their frequency, and you know this very well from feedback loops. Sometimes, if they're very close, for some periods of time, they're almost in phase. Some periods of time, they're out of phase. So we will see an emergence of a new time scale where we're going to see they're being in phase, they're being out of phase, they're being in phase, so loud. And you see that this is a new time scale because these frequencies were in milliseconds. Now here the time is in seconds scale. We can hear it very nicely. Right? So this is the new scale that appears because of interference. Okay, so waves don't exist just in time, they also exist in space. If you imagine throwing a pebble in a puddle, you will see that the surface of the water will have ripples. These ripples are in space. So now here, this axis is going to be space, and there's going to be a frequency in space. How this wave is changing? What tells you the rate of change in space is what we call a wave number. So this is an important concept to remember. Is really the analog of frequency or sound. And here we have a picture of one of these water bugs. We call this alfaiate in Portuguese. I don't know exactly in English. And when it touches the water, it's launching all of this ripples. This picture was taken in a very nice moment of time where there's two of them together next to each other. And what happens is that each one is launching these waves. And you can see that they're from different spots. So sometimes if I take this line here, they will be exactly in phase. So they will add up, have like double the amplitude. And if you take this line, they will destructively interference here, and we won't have anything. So here we have, again, this notion of uncertainty and the notion of interference. Here, uncertainty is the wave number, the rate of change in time. So in space. So again, if I know the wave number, it means that this wave is spread all over the space. So uncertainty interference are really properties of waves. They're classical. It just tells you that you have an amplitude and a phase, and when you add them up, it will be minded of that. And quantum mechanics is really the understanding that particles like electrons, light, photons are described by wave functions. So this has definitely been mind-bending, or the inception of quantum mechanics. But really, physics is an experimental science, and we just do math to describe the experiments, and these are the experiments, okay? So if you have an electron gun, you just send electrons. I mean, now send one by one through two little slits. Oh, and I just send one. It will go through one slit, and I'll find it on the screen here. Okay, but now I do it many times. I send all of these electrons. What's going to happen? It's instead of being like I will find most of them just behind these two slits, I actually find an interference pattern. I actually you see that the highest amount of electrons, they fall right in the middle of these two slits. It's really behaving like a wave, like you would have sent a wave. And it's exactly the same if you would have an experiment made with a laser. So if you would just send the laser through these two slits, you would see also an interference pattern in the screen, and that interference pattern, so you have the maximum here in the middle, and it will be extremely similar. So both light and electrons are behaving very much like waves. And the first problem that you get to solve once you go to university to study physics is the hydrogen atom. The hydrogen atom is basically a problem where you have one proton, positively charged, one electron, which is negatively charged. They have different charge, like opposite charges attract each other, right? This idea of a strong heterocycle interaction between the two. The electron wants to be close to the nuclei. And you want to solve this problem, and you actually find many solutions. Okay, so these solutions are what you know as atomic orbitals. So you can have a solution where it's completely symmetric around the nucleus. That's what's called an S wave. You can have higher harmonics of that S wave, an S wave, two S wave, three S wave, so on. You can have E type of orbitals with like higher angular momentum, so the electron is somehow making this. And this is really a beautiful description of all the possible solutions of this mechanical problem. What is extremely exciting is that just solving this very simple problem, of the hydrogen atom, we can understand so much about all the substances that we have in our world. So the periodic table, which by itself, just organizing it as it was organized, was a tremendous achievement in the late 19th century by Mendeleev. But when quantum mechanics came, we actually could understand why it's organized in the following way. Every single element, this number here tells you the number of electrons that you have around. And this basically will fill up these orbitals one by one. So if you have hydrogen, only this first one is occupied. So all of these orbitals, this here, it will be, the top electron will be on s orbitals, all of this will be on the p orbitals, all of this will be on the d orbitals. That is a lot we can actually say about just different elements of the world just by doing this. Just basis of chemistry is pretty much based on this problem. Now, every single orbital, all of these wave functions, these solutions come in different energies, discrete energies, which is like this very important part of quantum mechanics. So the lowest energy will be sky, so it's the one that you try to fill first. Then you will have some higher S into P orbitals at higher energy, and so on and so forth. And you can make one electron from here jump over there. You just provide enough energy for it to do it. And you can see that very nicely because you shine light. There's this, polychromatic light, visible light, all of the different frequencies. You see that only a few of them get absorbed by hydrogen gas. That's because that's exactly the energies that it takes for one electron to bump from here to here, and so on and so forth. There's another extremely important part of this, which is, if you look at this orbital, you can think of these points basically as timestamps of where the electron is. The electron is just quantum fluctuating from point to point. This is just one electron. I'm ignoring spin, but for those that don't understand. So the electron is just jumping around, and if it's higher density, then you see that it's more frequent to be there. So there is a notion of not knowing exactly what's the position of the exact electron once you know which orbital it is on. Okay? So if I do a opposite train of thought, which is imagine that I pin down electron in one specific spot, is displaced from the nucleus, displaced for the positive charge. I said what we call a electric dipole, because now you have a positive charge in the nucleus, your electron is a little bit displaced from it. We can ask ourselves, okay, how could I construct such a thing? Well, not come just from an s orbital, because the electric dipole has this expectation of where the position is always going to be zero. This is our symbols that we use to say what is the expectation value of the position of the electron in quantum mechanics. If I were to use a p orbital, it will be the same. Look, this p orbital basically tells you that the electron is bouncing around. Here it has positive phases. Here it will have negative phases. But one thing that I can do is I can just sum those two together. When I sum those two together in the correct way that adds the phase properly, you see that now most of the electrons are displaced away from the nucleus, from the positive charge. I was able to create a little dipole by mixing two orbitals. Now, there's an energy cost to this. It does not come for free, because mixing this electron, they are separated by an energy, so I need to pay that energy in order to create that dipole, create that displacement of an electric charge. It turns out that this quantum fluctuation, where the electron is bouncing around here and there, is basically telling you how easy it is for the electron to go far. So it needs to go, if this energy cost is very, very large, it would try to be very, very compact. Your electron cloud would try to be very, very small. So one thing that you could imagine, making the like this attraction stronger and stronger and stronger, you would expect this electron cloud to be smaller and smaller, so you have less uncertainty in the position. This is the variance of the position. I will use this symbol to talk about the uncertainty of the position. The uncertainty of the position will go like 1 over the energy cost of combining these two orbitals. It's quantum mechanics, so if I know the position, I don't want to know the speed, which means that if I make this orbital more and more compact, it will jitter faster and faster and faster. Okay, and this is so the speeds, the average, the distribution of speeds of this electrons in the orbital will go like something like the energy gap. So here it will be the variance of the position. So if you want to understand how light interacts with materials, you really want to talk about how light is absorbed, it creates these little dipoles, how it gets emitted again, and so it basically it interacts with the light with the matter by its electric dipoles. What happens when you have an electric dipole is that you actually emit it with different wave numbers. And what it happens is that effectively, when you have many of these dipoles, your light slows down. It doesn't change the energy, just slows down. That's the effect of slowing down the light. So here you have an insulator. It's orbitals. Because I'm shining light to it, I'm creating these dipoles. I am slowing down the light because I'm interacting with the light, and the light is bending. You can see it's the bending of the light, which is called refraction. Now, you can have a system that gets polarized by the light. You can have a system which is already polar. Water is a polar substance, and this has been, over the last few days, we have had a lot of water in the air. And I don't know if you saw this on Sunday, but this was absolutely gorgeous. The water droplets in the air, which are polar, they're interacting with the light a lot. They're slowing it down, they're causing it to refract. Okay, and there we'll see nice rainbow. So what is this refractive index, which is a property of this material, of the substance you are talking about, is really how easy it is to polarize your medium. It's really somehow reflecting how fat this atomic orbitals of this quantum mechanical uncertainty is of your states in this particular substance. So now we have to do a little bit of a more complicated problem. and to the point that, has been complicated to do to modern science, which is to talk about this electron localization in systems that have billions of atoms. And this becomes actually a hard problem. So now here on this side, I'm showing you this is a three-dimensional structure. It's in 2D, but we can try to understand it. So this is a three-dimensional atomic structure of rock salt, just a table salt, where you have sodium, chlorine, and which are in yellow. And on this side here, we have diamond, which is just composed of carbon atoms. And if I put my electrons, if I look at where the electrons are, these are insulators. They're completely transparent. Okay, so these electrons are very localized into small orbitals. If I look at, and they have about the same energy gap. So this cost of mixing orbitals is the same for both of them. But here, if you look at salt, the electrons are very much bounded to the chlorine. And if you look here at diamond, also very, very localized, but they're localized on the bonds. It makes a difference between what's called an ionic insulator to a covalent insulator. So this is electrons are living on the bond, so they're shared versus being held together by ionic interactions. There's too much negative charge here. Okay, now let's make a quantum mechanical experiment. They have the same gap. Which one you think is prettier and refracts light more? I rather have diamonds on my jewelry. So what is happening? Okay, how this, by having the same gap, why is they behave so, they look so different? This is because the refractive index of this guy is actually substantially higher. The refractive index, actually the best refractor that we have in like insulators of this sort. So the light is really bending a lot, bouncing around and hitting all of the very nicely cut boundaries and reflecting inside. And so for that, we need to understand, how do we think about the refractive index? Well, the refractive index is how easy you can polarize. It's related to this uncertainty of this size of these orbitals. It's very hard to tell the size of the orbitals when you don't have a point of reference, when you have an infinite crystal, which is the case here. But what turns out to be is that if you imagine tracking one electron, this will be mostly localized here all the time. While if you're tracking one electron in diamond, it will just jump between these different bonds. So the uncertainty in position is much higher in diamond versus in salt. So the problem is, how do we describe this mathematically? Okay, because when you have crystals and they're infinite, you have so many electrons. All of these electrons are characterized by wave functions. All of these wave functions, we need somehow organize them in some manner. The way that we organize them is by wave number. So it's by the frequency in space. So actually, all of the states of an infinite periodic lattice, they are completely delocalized. All of them are completely delocalized. Which means, we don't have, like in a hydrogen atom, only a few discrete levels. We have what's called bands, which are all these levels we have for each wave number. When we can change this wave number to anything, it's a continuous variable. So we can parameterize, we can have many, many different waves, what we call plane waves inside of this material, characterized by different wave number, have different energies. And this will be a typical energy spectrum that you would get. We know how to calculate these things very well. There's a lot of very good computational methods to obtain this old band structure of different materials. There's still an energy gap, so it's filled here. There's still an energy gap. Now we have this continuum of states. So now, what I told you, and let me rewind to the beginning of this talk. Wave number is the uncertainty in position. If my states of the diamond of any lattice have have a very well-defined wave number. So shouldn't the uncertainty in position be infinite? Okay. That's where we have a little bit of a problem describing this, where we have to go and bring in mathematics. Okay. So don't expect to completely understand these equations. Don't get worried about it. But let's just remind ourselves that this uncertainty relation, wave number is this change in position. I can reverse that. Position is this change in wave number. So I really, in order to properly calculate these uncertainties in position for materials, I have to actually care how these wave functions of these electrons in these materials are changing as I change my wave vector. Okay. And as you move around, so again, there's infinitely many wave vectors, and they form this space. You can form any space in general. In 3 dimensions, it will be 3-dimensional torus. In 2 dimensions, it will be 2-dimensional torus. But it forms a space, a continuous space, which I can parameterize all my different wave functions. And I can ask, how is the wave function changing as I change this wave vector? Okay? If it changes a lot, there's a big, what we call a distance between them, a big quantum distance between them. And it's so that's exactly what's going to parameterize this size. And it can also have a curvature, which means that if I change in X, I also change in Y. Okay, so in KY. So I will pick up the curvature of this space, of the space of wave functions. Okay. So if I were to very pictorial represent the difference of the photomechanical properties of these two materials, in rock salt, basically the wave functions don't care about the wave number. They're always kind of constant. And if I look at diamonds, it actually winds around, and it picks up all of these different loops. Okay, I don't see a time. So now I want to go a little bit further to understand two metals. Let me start with a simple molecule, a small molecule, which is benzene. Benzene is made of carbon. We love carbon. Okay, we want to do everything with carbon. So it's made of benzene, this carbon atoms, and each of them is bringing in an electron, and they are allowed to mix with each other, and we can calculate what are the wave functions of this molecule of benzene. And we find out that, the lowest energy state, it's going to be completely delocalized over this entire benzene ring, which means that, my electrons here, and all of a sudden here, all of a sudden here. So the size of these quantum fluctuations is the size of the entire system. It's very small, this system, but it's the size of the entire system. There is what we call condensed matter, or like a counterpart of this, a solid state counterpart of this. And this is a really beautiful material where you just have this repeating hexagons, honeycomb lattice of carbon atoms. It's one atom thick, and it's infinitely large, okay? And again, so all the wave functions are labeled this by these wave numbers. You have energies. This is the energy spectrum of that. And what we find is that, for the same reason that benzene, as instance, the quantum fluctuations of these electrons take them anywhere. Okay, so they grow infinitely big. So these electrons here can jump here and can jump here, can jump here. One way that you can think is the energy cost. Just remember this gap. The energy cost to polarize my system was the gap, and this gap is actually going to zero in this beautiful conical points, which we call Dirac points. This has been the entire field of research. It's granted the Nobel Prize in 2010. And basically tells you that electrons go extremely fast in this material. It's one of the best conductors we have. So we put an electron here just by putting little potential difference, and it just flies out to the other side. Not perfectly, but goes very fast. Why is this happening? Well, as you go closer to this point, these wave functions, the function of the wave vector, they have this vortex and they go extremely fast. They change extremely fast, which means that this uncertainty in position blows up. Okay. But the point to remember from this is that really these quantum mechanical fluctuations are something to do with the wave functions or with this in quantum mechanics. And really, this is the thing that we are trying to understand better and better. So graphene is an amazing material, and we thought we actually understood everything about graphene, but we have a new era. And this is a new era that started a little bit before it exploded, let's say, in 2018. I will explain you why. The idea came that you pick up a layer of graphene, of this monolayer, this one atom thick carbon lattice. We put another one on top, okay? Now you twist it. Okay, we'll do it again. And now you twist it, okay? So this is called the Moiré pattern, like Ed was saying before. You see the emergence, a little bit like in the interference before, but this is not quantum mechanical, this is the emergence of a new lattice, of a new periodicity in the system, which is what we call this Moiré materials and Moiré unit cells repeating patterns. So now, I told you, like graphene has this beautiful material where electrons are so delocalized. And if I have some of them in first layer, the ones in the next layer, and I allow them to talk with each other, I can get something different. This is what we get. They localize around this point. Okay, so all of them concentrated in a specific spot of this Moiré lattice. They form a new lattice. They form what's called a Moiré lattice. Now, notice that size of these orbitals it's much bigger than the size of the orbitals of the original carbon. We created some kind of like new orbitals which are extremely large. And this is not just fantasy. So here's an image of these orbitals measured by spectroscopy technique, scanning microscopy. You see here that these electrons are basically localized into these orbitals. And here, this is the important number. And this is on the scale of tens of nanometers, which is huge because the size of an atom is like an angstrom. This is much bigger. Now we need to understand the properties of these electrons on this new lattice. And this was a very influential paper, Bistritzer and McDonald, which they have proposed that, when you do this, these electrons that will go very fast in graphene, their energies get somehow changed and they become very slow. The point it's, we have some limit, so almost zero. And so they basically have almost zero velocity. So if I put it on one side, it barely goes to the other. It becomes a terrible conductor. It started with a wonderful conductor, which is graphene. It became a terrible conductor. Interestingly enough, there's things about it. So let me just first explain how it became a terrible conductor. Okay. So imagine I have an electron here that wants to get there. And it's really forget about this the two layers. It knows how to move at its original velocity. And it goes very fast. And it goes boom, it goes around, gets there. But it could also go this way. It could also go in any other possible way. It's quantum mechanics, which it goes in all ways. They're all interfering with each other. So we need to somehow find what's the probability of the electron from here get there. From this cloud, get to that cloud. And when we sum it all up, basically it never gets there. this destructive interference. It just never actually goes to the other side. But the effective velocity at these very long distances, which is really what we need in order to conduct electricity in this metal, just goes to zero. So it's a terrible metal. This is coming from interference between these electrons and these very large systems. Okay, so now we can ask ourselves, let's pick up one electron, like we did with diamond and like we did with salt. Let's pick up one electron and kind of see where did it go. And so it's just jumping around. Turns out that it's kind of shared between this fidget spinner, 3 of these orbitals. Okay, it goes boom, 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 boom. There's no velocity, net velocity. There's no average velocity, but there's because it moves in all directions, right? But there's an uncertainty in the velocity associated with their local kinetic energy. So it just jump around. It actually goes here, goes there, goes there. It moves around. It moves with one-handedness. It actually decides to go this way. This is very interesting because even though it's really compactly localized into this object, it's very fast. So there is very light. They're very different. As if you look at long distances, it's very heavy because it doesn't move. Here is very, very light. Because this uncertainty, which comes from geometry, is very large. Okay, so this is where we're getting this piece of information. Now, this is where also the X being related to the Y of the geometry matters. So there's a certain vorticity, this handedness that appears, which means that there's a little bit of an angular momentum to it that is important. And again, if you were to look at the refractive index, would be also associated with these geometric properties. Even though at long distances, we found by calculating energy spectrum and so on, that electrons are very flat, velocity is very slow. So there's some of this in this handedness, there are some other handedness. The really important key point here is that this is the reason you just cannot make an orbital like this out of an hydrogen atom. You cannot. This is completely new orbital. It's part of a different, different periodic table, and it's really can have rather unique properties. And this is really what we like. This is what we live for. To find systems in which just by having so many particles interacting with each other and talking to each other, we get fundamentally new things, fundamentally new physics. And this is what's supposed. This is a very famous article by Phil Anderson in '72, where basically is making the case for field condensed matter, for saying that you should just look at the elements individually, will not learn anything about how so many when they all come together. But okay, and this is not maybe so exciting that we have this new orbitals, this local structure. We want really something really exotic, really new, something that we were not expecting, made out of carbon. This carbon, it's nice, but if we want to think about really exotic phases of matter, it doesn't seem to show a lot of things. But we now have a new tool. We were able to slow down these electrons very much. And we have the separation of scales, where they're fast locally, but they're slow away. And one thing that they also do is because they interact with each other. And if they are all kind of occupying the same spot, they don't want that. And so they want to do some other things. And it might be that now in these new platforms, we get some truly exotic quantum phases of matter. Let me show you one. And this basically is one where we're putting electrons in this lattice, and they decide to only take one of the handedness, not the other one. This can happen because of the interactions. But choose just one of these circulations, one of these handedness. Now, this is a very intriguing situation because, of course, all electrons are very localized. They don't really move far away. They around here, but they don't move right away. The thing is, the very interesting thing is when we cut the sample. So I'm basically what I'm doing, saying, okay, I'm cutting. My system does not go all the way. I have boundaries. I will end it, terminate it. And when I terminate it, I created all of these orbitals out of interference. So now I will change, I will mess up a little bit my interference, right? It can be, and well, it happens, that only one electron goes around all the way. One, not many, one. That is absolutely insane. Okay, this is a phenomenon that we know. Okay, it's not a new phenomenon. It's a phenomenon we know for electrons in a strong magnetic field, not in carbon on its own. This is not something that we knew. So that has been experimentally seen. Okay, so this is the experiment from Andrea. Here, what we see is that the resistance goes. So I'm basically now putting a contact into this big object. Okay, and I'm feeding electrons here to this side, letting electrons enter in this channel and go the other side without any possibility of scattering back. Okay, so they cannot ever go back. So you'll see that there's zero resistance for the electron to go on the bottom channel. But another thing that you see, which is this, and this is, it should look here. This zero is important. You should also look at the resistance measured like that. If I put contacts here, the reason is you'll see that it has one quantum of resistance. What does it mean? That I know that one electron is here and no electron is here because I want to take this path. If I was to reverse, I would have that electron going over here. And that potential drop, because of that one electron, I can see it, and it's exactly the quantum of charge of one single electron. This is, it's a fascinating phenomenon that we've learned from the 80s, from Localization, that first time that it was measured in electrons in a magnetic field. But see this as just spontaneous happening in these carbon systems is absolutely fabulous. Now, this was the experiment that got everybody excited about the field and that really created the field of Moiré materials, I'd say. It was announced in the March meeting. You can see this picture in 2018. What did they see? Superconductivity. At this specific angle, you get superconductivity in the systems. Now, okay, we start with a pretty bad conductor. We lower the temperature, and all of a sudden it does not become like a good conductor. It becomes a perfect conductor. Zero resistivity everywhere, not just one channel, everyone goes. And so if I put electrons, they always come out on the other side. This has been extremely exciting because nobody would ever imagine seeing superconductivity in graphene or any of the carbon types. So this caused a lot of fuss. There has been already prizes given for this work. So Pablo Jarrero has done this experiment, which is really, truly groundbreaking. So let me just, we're still not understanding what really happens. Actually, that's one of the reasons we are all here. But I can tell you that geometry is important. Okay, that's all I want to tell you. So electron doesn't want to go by itself because interference, we already shown that it just does not go. What if the electron really wants to move? Okay, what is it going to do? It's going to pick up another electron on the way. It's going to form a pair and they will not leave. They will stay together. Okay, they stay together, and now if they go together by forming these bonds, it's called the Cooper pair. That's the jargon. And then they can move freely. And actually, the velocity that is set for this pair to move is set by the quantum fluctuation velocities of these quantum fluctuations. Is really, or this mass associated with these quantum fluctuations is not by the interference. Now these guys can be mobile. They can be mobile. They were fast. Many of them are formed. They all move around to the point that they do one of the our, let's say, really fantastic quantum phenomena, which is they all lock to each other, and they lock to each other, they carry each other. This is, called and then making a condensate. That is the phenomenon of superconductivity. They make this soup. All of them, they will go as one. Now, all of a sudden, what actually carries charge in your system, not this one electron one by one, but rather it is this macroscopic quantum state, soup of electrons paired up, that if I hit on one side, you all move. So no matter which electron I put here, it always comes out on the other side instantaneously, right? And this is the phenomenon of superconductivity. We see it in this system. It's the quantum geometry must play a role. But you don't see only that. I think we see basically every quantum phase, exotic quantum phase that we have come up with in condensed matter. This is the phase diagram of magic angle. It's called this magic angle twisted by layer graphene. We can twist other materials, other low-dimensional, two-dimensional materials. We can change how many electrons we have. We can change the angle, and we will have really a zoo of different quantum phases, some which are unique, they're new, that we have discovered. And if we had no quantum fluctuations dictated by quantum geometry, this would just not be possible. We would have frozen our electrons in place. We would just simply not interact with each other and give us interesting quantum phenomena to think about. So let me thank my group, particular Nish and Ilya here, who really have been instrumental in understanding concepts like the refractive index in terms of quantum geometry, which is really just fascinating to me. And thank you all for your attention.
Questions, please.
Yeah. So if I remember back to high school chemistry, we could always talk about macroscopic chemical properties of an atom, like orbitals.
Yes, absolutely.
And these twisted, these wire materials, they do kinds of orbitals.
Right.
And they also have different macroscopic chemical properties.
Yes. So basically, your orbitals are now, instead of it's not really you cannot talk about these discrete levels. You talk about these bands. And in a sense, this is almost behaving like a level, behaving like one orbital. It doesn't care about wave vector. So one thing that you can think about is that you can twist different materials, and you'll get different properties of this band, which is very flat, which behaves like a little orbital. And this happens. So if you were to take instead of graphene, you were to take a transition method like alkylogenide, you will have slightly different physics. But there's no systematic way of talking about these different orbitals. There's the mathematical way, which is describing their geometry.
Can you speak to the practical application of what you've been discussing today?
Well, yes. So I think that it's really important to have some kind of rules of thumb to understand how materials are going to behave. Okay. So as far as I know until now, there's really serious computational approaches to calculate properties like the refractive index of materials. But it's very hard to look at the band structure and say, oh, this is going to have a very high refractive index. This is very important. Or if you want to engineer a system, like a photonic system, that will have a very high refractive index for whatever cavity mirrors, whatever you want to do engineering with these materials, with these metamaterials. And this is an important information to have in mind, because you will really completely change the optical properties of your system if you engineer not only the energies, which that's the traditional way of doing things, engineering the energy spectrum, but engineering the wave functions in some smart way. That is the core geometry. But when it comes to these Moiré systems, I think these are still at very low temperatures. We are really just discovering fundamentally what kind of different phases we have. I showed you a phase where electrons pair together in superconductor. There's also phases where electrons break apart and make fractionalized particles, which have fractional statistics. This could be used as anyons for quantum computation. But we are really, this is a young field. The Moiré part is a young field, which I think it will have a lot of developments in the future.
What causes the graphene electrons to stop going in circles and beating a bad conductor to pairing up?
That's the question. So really there's usually if you think about normal all metals superconductive, there means low temperatures enough. What happens is that we need to have some glue bring electrons together. Okay, so we need some attractive interaction. Now electrons have opposite charge, the same charge. They repel each other. They don't attract each other. We need to think about mechanisms that will bring them together. The normal superconductivity or normal conventional conventional superconductivity. What happens that an electron is passing through the lattice. It's actually moving the lattice because the sites, the atomic nuclei, they're positively charged, so they try to go back. Then they move very fast. It creates a charge puddle, positive charge, brings in another electron, and they kind of get paired up. There is one that's called phonons coupled are the glue. Now, in this problem, we still don't understand what's the glue. That's scientific question which we really want to we're all here to understand better. Yeah, but it's why it's also so unexpected that it actually happened.
What are you, is there any kind of sort of theoretical hypothesis or work going to get into trying to explain the phenomenon of boson or electron based on its constituent smaller particles?
I'm not sure I understand completely the question. So this is
On conductive.
so electrons. You were thinking about the so this electrons are fermions, which means that they have a specific statistics that do not allow them to have the same quantum state. When they pair up, they form bosons. So they behave like light. They don't need to conserve particle number. They can condensate, and all of this is going to happen. So that is somehow important to remember when you break them apart with a new phase of matter, which fractional normal Hall effect, which we've also seen in the systems. Then these things are neither fermions or bosons. We call it anyons for any phase. It's like anyons, and this can have really interesting properties. So when they're not antisymmetric like fermions, they're not symmetric like bosons. Will gain some random phase. Then I'm not sure if it was exactly your question.
I don't know enough to ask you more specific.
We can talk later. I'll be happy to talk more.
That one electron that's removed went in the opposite direction.
Oh, that was me making a picture. So really, there's no net velocity. There can be a net vorticity, and every time you have net vorticity, you kind of break. Okay, so you can tell the difference between left and right. So you cannot tell the difference between left and right in anything made out of carbon. So there are these, and then there's another set of orbitals which are the same energy, which have the other. But this is really me just presenting how things jitter around.
In the other picture.
Yeah.
There's that one electron that moves freely.
Mm-hmm.
That one seems to be done in the direction.
Yeah, it chooses the same direction as this. You can think about it as skipping its orbits. You cannot complete the orbit because you are missing some molecules here, and then you just jump around. There's just one electron that will go.
That's my question. Is there a connection between superconductivity and electromagnetism? Or is anybody thinking about that? And does the environment that matters in affect on these things that we can observe the way that electrons interact and vice versa, as far as like if you were to do this on a macro scale, would they that influence the environment? So say like if you have a field of gravity or a flat field of gravity.
So the first question, both magnetism and superconductivity, they're interacting. There's quantum phases of matter, which appear because of interactions. Like in general, if you decide electrons decide to be a superconductor, they don't necessarily decide to be magnet. There's some exceptions, but mostly you have the superconductors or magnets. The electron does one or the other. Sometimes it jumps between one and the other by changing properties like pressure or something like that. Now, the other question was,
If you run the same experiment and building gravity or out in the vacuum of space, do you observe different effects?
so all of this all of this understanding does not take into consider. Actually, this is very simple. Quantum mechanicals at zero temperature, no environment. So this is just we just solve for this particular carbon atoms and their orbitals and how they tunnel between different atoms or interact with each other. We just don't even see. Gravity is a weak force compared to the forces that make these electrons assume this particular structure. So it will have no bearing.
Question? Good. Just that good.
Thank you. I'm curious. Last summer it was all the LK. What was it, 66 or
99.
But I'm curious if you put on your science fiction hat for a second in the proliferation of graphene, what are the 10, 20, 100-year impacts in your mind, civilizational impacts of a material like that? Conduction. Yeah.
Oh, having superconductors at room temperature? That would change a lot of things. You know, that would change a lot of things. You know, most of it, we want to transmit electricity from one point to another, we're losing 40% of the power as it go. You know, so if we all the time we're now with more and more data, we need to store it in different ways. We need to transfer this information one way or another, always with electric signals. So the amount of energy that we would save would be completely, outstanding and completely changing everything. So there's no, as far as I see it, there's no fundamental reason why we don't have a superconductor at very high temperatures. Unfortunately, that wasn't it. But I think it's what we're learning a lot from these new materials, which are very tunable. So it's really allowing us to have a playground of materials where superconductivity appears in different ways, and that can actually help us to search for superconductors because superconductors, you bump into them. You don't usually predict and go and find. So most of the first superconductor, the high temperature superconductor, like the cuprates, they were just found. So there was no real prediction of them. And I think that we'll try our best. Yes.
Well, for coming.
Thank you so much.